Okay, so it's been a long time since I've done the calculus unit. I'd left off at number 10 for 4.3. And what they go on about here is the sketching algorithm, which is really important to learn for sketching because otherwise you miss parts. So you're looking for discontinuity, so that would be asymptotes, horizontal and vertical. And generally speaking, when you're dealing with something that has a polynomial at the bottom, you're going to have possibly asymptotes, except in this case, which I circled, but definitely in this case you will, and this case, and this case. So you're going to have vertical asymptotes and most likely horizontal or diagonal. There's another term for them, asymptotes. So you're looking for those. Find both intercepts, or there might be more than one intercept. Generally speaking, the numerator will dictate the intercept because the bottom, other than the restrictions, doesn't affect 0. Like if you take 0 divided by 9, it's going to be 0. So really it's the top part of any fraction that dictates your zeros, which dictates your x-intercepts. Find any critical points, so you use your knowledge of first derivatives and second derivatives. The first derivative will, when it is equal to 0, will dictate a max or a min, but you won't know which. A second derivative, if the derivative, I believe, comes out minus, I think it was, we're dealing with a max. We'll get to that for sure. And if it comes out positive, you're dealing with a min, but I might have had that mixed up, but we'll see when we get there. There they go into the detail there. Test the end behavior, so yeah, put like a million in for x and a negative million in for x to see what it comes out with, and there's another technique to use for that. Construct an interval of increase or decrease table, and that's what this is. Now I actually prefer, and it looks like I got the copy down incorrect. Let's see if it comes back. No, it doesn't. And I actually prefer to have the values. For instance, let's say you find there's a vertical asymptote at -3, x minus 3. Let's say you also find out it crosses the x-intercept, or sorry, a vertical asymptote at x is equal to -3. Let's say you find there's also an x-intercept at, let's say, 0 and 2. And let's say you find another vertical asymptote at 3 or 4. I prefer to set up my table like using those as measurements. So then I would do this, and I would put in a top chart here, like that. And then I would use those exact lines on the graph to set it up like that. And then in the boxes, the box I've created at the top, you would put in an x value that is smaller than -3. Here you would put in an x value that is between -3 and smaller than 0, because it's between those two lines. Here you would put in an x value that's between 0 and 2. And here you would put in an x value that's between 2 and 4. And here you would put in an x value that's bigger than 4. Then you would put in, let's say these were the terms at the numerator. I'm even going to put a -5 in there. X plus 3, even though that's not necessarily right. X, it's probably x minus 2 just to be fair, but these aren't accurate to the graph I've created. I just want to show you some of the terms, and let's say the bottom term has the x plus 3 and x minus 4, which would create the vertical asymptotes. You will then want to take each of these terms, including the -5, and put them here, right outside. Because whatever the x value in there is going to dictate whether it's minus or positive when they all multiply and divide. Now, fortunately, division and multiplication are pretty much the same process for determining if it's positive or negative. Then at this positive bottom part, you would go positive or negative question mark. And you could put a whole new case here. And boom. And then I would just finish out dividing it up like that, like that, like that. And sorry, I didn't do that last one very straight. There we go. There we go. And a couple of these lines here like that as well. Now, obviously you can do it as neatly as you want. I'm a little bit messy. But let's take, here we're trying to pick a value for x that's smaller than 3. So let's go with -4. Well, this -5 will automatically create a minus. So we're just going to create a minus symbol there. If I plug in -3 into here, it's clear we're dealing with, or -4 into here, it's clear we're dealing with a minus. -4 into here, it's clear we're dealing with a minus. A -4 in here, we're dealing with a minus, and a -4 in here, we're dealing with a minus. It's essentially, what will the result be if I put -4 into these brackets? And I got all minuses. Then you multiply it. Minus times a minus is a plus, times a minus is a minus, times a minus is a plus, times a minus is a minus. And you'll discover when there's 5 minuses, it's going to come up, or an odd number of minuses, it's going to come up as minus, and when it's an even number of minuses, it's going to come up as plus. So in this case, we got a minus. This will instantly tell you that when you're graphing, all values to the left of this asymptote will be below the x-axis. So you know it's going to be drawn like that, or something like that. You would also test your extreme negative infinity. So there should actually be another column in here that's called negative infinity, and another column in here that's called positive infinity. And that's when you take a huge number and put it into here to get a value, an actual value, to see if it's coming up to the horizontal asymptote, or if perhaps the curve is instead doing, something like that. So it helps to take the infinity columns as well. So that's one I should have included. But I'm just going to stick to positive and negative. Then you pick a number here that's between -3 and 0. A good one would be -1 because it's easy. Obviously the -5 is going to be minus. So you can see the -5 is contributing a minus no matter what. So we would put in a minus for all the boxes. So that's important, because if you forget the -5, you will have the opposite result down here. But anyway, -1 into here, we get a minus. -1 into here, we get a minus. -1 into here, we get a plus for the first time. -1 into here, we get a minus. We can see we have an even number of minuses times a positive. It's going to come out as positive. And usually your graph will flip back and forth, but not always. So be careful. Now, what's a good number over here to take? 1. So obviously we got a minus for the -5. We got a minus for the when it's in here. We get a positive when it's in here. We get a positive and a minus. Notice it's flipped back again. We get a minus, and so on. So a number here is 3. We get a minus, a positive, a positive, a positive, a minus. So here we get a positive. It's flipped back again. And finally, just take a 5 here. You get a positive, a positive, a positive, and a positive. But this first minus makes it a minus. Now you know exactly how your graphs, which side of the x-axis they'll be on, over and over again. Just remember that, some of these are x-intercepts, so this last one might be doing something like that, and then this last one might be doing something like that. This will greatly help you figure out how to graph, and that's what they want you to do here in number 10. So let's try it. It's a long process, but you will get very, very accurate results. So we're going to start with this very simple one. I might only have time to do number 10 right now because something's calling me. And I'm going to just copy this process just so I don't miss any steps. There we go. All right. So let's work on let's just put in a graph here. Okay. And I might have to delete some of this stuff to make room, or I might have to keep some on another page. And let's work on the easiest thing, the vertical asymptotes. Well, when this bottom is 0, I can't have a 0 down here, so 2x plus 5 cannot equal 0. Cannot equal 0. which means 2x is equal to minus 5. I've put the minus 5 to the other side, which means x cannot equal minus 5 over 2, which is 2.5, which means I'll have a vertical asymptote at negative 2.5. Let's put it right there. And if you're going to draw it properly for your teacher, you put little dots in here. You would even label it. X is equal to negative 2 over 5. Was it 2 over 5? 5 over 2. Okay? And now you know that something's going to happen on this side that might be different to that side. And the next thing you say, okay, well, there's no other ones, but what about when will this whole thing equal to 0? Well, because that will dictate x-intercepts. Well, you're going to discover the numerator has very little to do with that unless it happens to hit negative 5 over 2. When I put this equal to 0, I bring this whole thing as a bracket to the other side by multiplying it by 2x plus 5, 2x plus 5 over 1 on both sides. That's how you get rid of any large grouping. And because these are essentially in brackets, you can treat them as like one unit. And when I multiply the other side with 2x plus 5 over 1, it clearly disappears into 0. That's why the denominator has very little to do with the x-intercepts. So you're left with this. Now if I bring negative x to the other side, which is the easiest thing to do, I see x is equal to 3. So that means when 3 is in this equation, it's quite clear that it becomes 0. And since 3 is not the vertical intercept, I don't have a problem here. So that means there's a dot right here on your graph at 3, 0, which is going to be a little bit further over compared to 2, 0. Now, you should use graph paper. That's another thing. So you put a little dot here. And that means you know the thing is going to either touch or it might go through there. To see if it goes through, you have to test on either side, which is why we create that chart. But anyway, we know that there's a dot x-intercept there. So we've gotten discontinuities. We found vertical. What about the horizontal asymptote? How do you determine a horizontal asymptote? That's sort of the step I should have done in step 2. Well, that depends if the powers up top are the same or the different. This is x to the power of 1, and that's x to the power of 1. Let's rearrange it in terms of minus x plus 3 up top and 2x plus 5. Well, the numbers don't have anything to do with the horizontal asymptote over here. So these are going to be ignored. But the numbers in front of the highest term do. So I have a minus 1 over 2. So it's a minus number, which means I have a horizontal asymptote. When the x's are the same exponent, it's all about the coefficients in front. So that means I have a horizontal asymptote, which I should have done first, at y is equal to negative 1/2. And you can color it differently if you want to do your horizontal asymptote slightly different. You should do the same sort of thing to show that it's not the x-axis. And there you go. Now, excuse my roughness. And you should also label it, just so you don't forget. Y is equal to negative 1/2. The other thing you want to do is very few, but sometimes, the graphs, as in this case, might cross through. Or it's quite likely that this graph will probably do that. But to see if it crosses through, you now have to make the entire thing equal to negative 1/2 to see if it does. So just remember that's negative 1 over 2. Negative 1 over 2. Okay, we're going to start by multiplying this whole thing by its reciprocal on both sides. It's going to go up to this top, and it's going to disappear as a numerator, or as a denominator on this side. So this whole negative 1 is multiplying these two x's and this plus 5 by negative. So I'm going to get negative 2x up top minus 5 all over 2. All over 2. So that's that's going to happen there. Well, obviously I have to get rid of the 2, right? So I'm going to multiply the right side by 2 over 1 and the left side by 2 over 1. And this whole thing has to be treated like a bracket that gets multiplied by 2. When I multiply by 2 over 1 on both sides, it cancels out. That's why you're doing it. You're getting rid of the denominators, essentially. So on the left side, I can see I get 6 minus 2x. And it's quite obvious that when I get the x's to the same side, I get minus 2x plus 2x, and they're going to disappear. So you're going to get 0, and the number you're going to get it equaling to is negative 11. So when the x's disappear like that, you can say, oh, now that's not realistic of anything, so that means my graph never crosses the horizontal asymptote. So right there, no, you can say does not cross somewhere. You should take note in case you forget it or get interrupted. Does not cross horizontal asymptote. Find both the intercepts. Okay, well, in this case, there's just one. By the way, it would be good to know when it crosses the y, and that's what they mean by both. It crosses y when x is 0. So when x is 0 here, or in the original one, when x is 0, I get 3. When it's 0 down below, I get 5. 3/5, which means it crosses right here. And I should probably have done the thing in a different color, but anyway. It crosses right here at 0. 3/5, which is less than 1. So it's quite low. And you should mark it. 0, comma, 3 over 5. What's 3 over 5? It's 0.6. So I'll just mark it as 0.6 for now, even though 3 over 5 is sometimes more accurate, which tells me I'm probably going to be dealing with something like this. But just remember, it's going to go through 3 over 1. So it's probably more like this, if I'm fair. It's pretty accurate. Pretty accurate. Let me make it in blue. There we go. And that, oh, and we'll try it one more time. There. And that goes through the 0, comma 0.6 and the 3 point, comma 1, 0 essentially. It's hugging the horizontal asymptote. And we know it's on this side automatically because when we found the asymptotes and the x-intercepts, we got these numbers. You'll discover now if we put 3 into our grid higher than 3, we're going to get a negative number because it crosses. And generally speaking, we know this is true because it doesn't behave like, it'll never behave like that. It's always going to kind of hug the asymptotes on either side. It might cross the asymptote and then hug on the underside sometimes, but that's the behavior of it. And the more you do them, the more you'll realize it. So just the question is, what happens over here? And that's what our chart is for. Find any critical points. So that means we have to take the derivative. And here I'm just going to get rid of this for now. And you have to go back to your rule of quotients, or you can use the product rule. Personally, I like the product rule, which means I can convert this, and I'm just going to put the x in the right order, to this, plus 5 to the minus 1. And that's just a way of saying, okay, I've got a denominator. Now I'm going to, if I use the product rule, I can take the quotient, the derivative of that, and just times it this, and add the derivative of this, which I have to use the chain rule, times that. Well, for this one, the derivative of minus x plus 3 is just minus 1. And since I'm timesing it the original factor, that just ends up being this, minus 1 over the original thing. Okay. Now I've got to figure out what the plus is. Okay, plus. If I take the derivative of 2x plus 5 to the negative 1, I first do the chain rule. So I get 2x plus 5 to the negative 2. Then I have to multiply, take the derivative of what's inside, so times, what's the derivative of 2x plus 5? It's 2. And then I have to times it, the original numerator, minus x plus 3. And that's the quotient rule. What does this part become? This simply goes down to the numerator as a square. That's what the minus 2 does. So I can get rid of it and just multiply out my numerators now. Minus 1 times 2 becomes minus 2. And minus 2 times minus x plus 3 becomes plus 2x plus 3. Sorry, minus 3. And there, I've got my new numerator. Now, you might say, well, that's not really useful yet. And you'd be right. And the only problem with them is they are two different fractions. This has a numerator of 2x plus 5, and this has a 2x plus 5 squared, which means the only thing missing which would make them the same fraction is a 2x squared here, right? That's the only way you can add fractions, is when their denominators are the same. Well, how do I make that left denominator the same as the right denominator without changing the fraction? Well, I simply multiply it by 2x plus 5 over 2x plus 5. That will automatically make my denominator 2x plus 5 squared, which is what I wanted. I'll try that again. Okay. And it'll make my top, what happens when I multiply 2x plus 5 times minus 1? I get minus 2x minus 5. Great. And sometimes they cancel out, sometimes they don't. Now that they have the same denominator, I can essentially make a great big long line like that and simply add or subtract the common terms up here. Minus 2x plus 2x, it's obviously going to disappear. Minus 5 minus 3 is minus 8. So we're talking about a number over that denominator. Now, it's quite simple now. That is the first derivative of f of x, and you would mark it down on your sheet of paper somewhere. F prime of x is equal to that. You'll also want to take your second derivative, which, interestingly enough, will be much easier to find any critical points. And I can pretty much say that we probably won't find any critical points because it's a number up top. But to find where, if there is a flattening in the curve, you would set this to 0. So I'm going to set it to 0. And obviously when I multiply both sides by 2x squared plus 1, 2x squared over 1 on both sides. I can't put it over there, but it's over there. This is how you get rid of the denominator. It'll cancel out here, and when it multiplies 0 over here, it'll become 0. So I'm left with this. Now what does that tell you? Minus 8 equals 0 can't exist, which means this thing will not have a slope of 0 anywhere, which means it does not have a max. And that makes sense when there's only one asymptote like this. It generally looks like a normal rational curve. It'll generally look like that. And when it looks like that, you'll see there's no real bottom point of these curves because they just keep trying to approach the asymptote. They don't curve back up. So generally speaking, when you just see one term at the bottom like this, you're not going to have a max or a min, which is when the derivative does equal 0. If you don't have a max or min, you don't have to take the second derivative because the second derivative will just tell you if it's a max or min. There is no max or min, no need to take the second derivative. However, this is an excellent exercise for practicing derivatives of rational functions because they're hard to do. We found no critical points, so I'll just move on. Use the derivative test, we did. Test the end behavior. So what happens here, just to make sure it's on the underside of negative a half, in other words, it never gets higher than negative a half, we would put in negative a million here. Now that's how I do it, but here's a smarter way. So I'm going to reorganize it in order. Minus x plus 3, and I'm going to put 2x plus 5 at the bottom. What happens if I take out as many x's out of this? In other words, factor out minus x out of it. Well, I get minus x, and factoring that out, I just get 1 plus 3 over minus x, which becomes minus 3 over x, right? If you don't understand how to do that, I'm just essentially dividing all those terms in the bracket by minus x and finding out what's left. And what you should, if you do it correctly, when I multiply this out, minus x times 1, I get minus x times minus 3 over x, I get plus 3. You should get what you started with. All right, what am I going to factor out on the bottom to get rid of all the x's? I'm going to factor out 2x from this. I'm going to treat it like a bracket. I'm going to factor out 2x. When I factor out 2x from the first term, I'm left with 1. When I factor out this next one, I'm left with 5 over 2x. So that's what I'm left as a factored version. Now, you can see that if this factor is divided by negative gazillion, if this little fraction thing is divided by a gazillion, 3, negative 3, or plus 3 over a gazillion becomes a very small number. So it essentially doesn't exist when x becomes huge positively or negatively. Doesn't really matter. It just essentially almost becomes 0. Whenever 5 is divided by a million, it pretty much becomes 0 as well. So we're really just dealing with 1. Now we can look and we can substitute negative infinity into this, and we see that we end up with positive infinity. And what do we end up at the bottom? We end up with negative infinity times 2. So since the infinities cancel out, we're left with plus 1 over negative 2. We're left with negative a half. And keep in mind that this is plus a little bit number. And that's a good point, actually. So that's going to be times what was in there. I want to go back to what was in there. It's essentially going to be subtracted. Negative 3 over a million is going to be like 0.000. Let's just do 100.03. And when this is 100, it's 5 over 200, which is 0.0025. So 25. So it's clear that this number is slightly bigger, but it's subtracted from 1. So we're going to have a number that's less than 1. And this is added to 1 and multiplied, added to 1. So this is going to be slightly bigger than 1. So this number is going to be slightly smaller than 1, and this number is going to be slightly bigger than 1, making this slightly bigger and slightly smaller, which tells me that I believe we're actually going to be on the top side of minus a half. But it still tells me I'm hugging minus a half one way or the other. To find out which side it is actually on is, and I'm just kind of getting rid of this stuff to begin with, we make the table. So essentially all we've learned is that it approaches negative a half, which we kind of know already. You don't have to do that 3 over 5 thing. You can just make this table. And in this table, I'm going to go back to black. You're going to make, we're going to say negative infinity. We'll just put infinity. And then we're going to put, what was that asymptote? We're going to put minus 5 over 2 here. What's the next thing? Is it a vertical asymptote or we might as well put actually the y-intercept isn't important. It's where it crosses the x-axis. So next we're going to put the x-intercept. And then we don't have any other horizontal information, so we're going to put positive infinity over here, just to give it a rough idea. Now we're going to take each of the terms. There's only 2. And we're going to put it on the left, like this. And then we're finally going to say at the bottom one, is it positive or negative? And I'm just going to lower this one more thing, like that. And I'm going to add it like this. I'm just going to add positive infinity in the last chart. So in this box, I'm going to have I'm going to make x smaller than minus 5.5. In this box, I'm going to make minus 5.5 in between smaller than x, but smaller than 3. In this box, x is going to be bigger than 3. And of course the plus infinities and the negative infinities in the last box. Then I just make a row for each of the things I've created. So negative infinity, we've already determined that it comes out to roughly negative a half, which doesn't tell us exactly what side. This, however, will tell us whether we're on the top side or the bottom side of that. And you want to take it right close to the asymptote, because as it crosses it actually doesn't. It only crossed x-axis once. So this actually probably, now I'm thinking it's definitely going to be on the underside, because we'd have to cross the x-axis here if it was on the positive side. So we're probably going to see a negative here. So we're going to take a number that's less than minus 2.5. Let's take minus 3. So here when it's minus 3, we get a minus number. Here when it's minus 3, it becomes minus 6 plus 5. We get a minus number. And it becomes positive. So check your values. Actually, I did something wrong here. When it's a minus 3 here, it's 3 minus minus 3, which becomes a positive. And when it's minus 3 here, it becomes a negative, which means we have a negative. So you can see how easy it is when they're in the wrong order to screw that up. I would rather subtract negative 1 out of it and have x minus 3. And that's a proper factored form, which won't screw it up as much. Because I see I'll get minus 6 times minus 1, which would make a positive. So that means I'm on the negative side, which it means now helps me graph it. I know it does not cross the y-intercept, so I know I can just hug the asymptote. So I've pretty much done the graphing for this one because it was so simple. It's going to look something like that. And if you really wanted to, you could find a couple values here, a couple values here. But we've already determined it doesn't cross the horizontal asymptote. It only crosses the x-axis 1. So this is pretty accurate. And we've already determined negative infinity. Let's determine what happens when it's between these numbers. The easiest number to put in here is 0. So when I do 3 minus 0, I get positive. 2 times 0 plus 5, I get positive. It's clearly positive. So that means between the x-intercept and the vertical asymptote, it's going to stay on the positive side until it reaches the x-intercept. Then when x bigger than 3, we'll take 4. When it's 4 here, we get negative. When it's 4 here, we get positive. And obviously, the whole thing's negative, which means after the x-intercept, between the horizontal asymptote, it's going to stay negative on the graph. And of course, if we take positive infinity, we're going to discover it also reaches negative half. So to do that, you do the same thing. You sap out negative x up top, 2x at the bottom. When it's positive infinity, this becomes negative infinity. This comes positive 2 infinity, which factors out to negative a half. So it just tells you that it's approaching negative a half. That helps to avoid screw-ups. And that's the end behavior. Construct an interval increase-decrease table. That's what that is. And sketch the curve, which we've done as we go. So there you go. That's an excellent way of doing it. And I'm probably, as I go here, I'm probably going to miss some steps. I didn't bother taking the second derivative, and I probably should. So let's just look at this. Can I simplify it? Do I have any information right away? Here's some information right there. When x is 0, it's going to go through minus 10. It would help if I factor out this, right? So I'm going to try to use synthetic division. And I'm talking about plus 36 and minus 10. And I'm going to start with my basic factors. 1. And generally speaking, on a test, they're not going to give you super impossible unless your teacher really wants you to get good at fractions. And if you don't remember how to do synthetic division, you better brush up on it. It was in functions. And you can see 1 and probably minus 1 don't work. So I'm going to jump straight to 2. Because if I find 1, I'm pretty sure I'm going to find the rest of them. 4, minus 11, minus 22, no, 14, 28. So no, so maybe minus 1 should be something I check just in case. And then I'll go to minus 2. Nope. And generally speaking, I think minuses won't do it because it produces a minus in the last number. That's way too big. So I'll go straight to 3. And I'm suspecting it's going to be a half now, which is kind of mean of them, but whatever. Either that or I might have made a mistake. Oops. Yeah, I'm going to check, just check 1 again. Even 2 again. Minus 13, minus 13, 26 doesn't work. And look quickly for grouping. And there's no real grouping going on. So let's try a half. One thing you can do is put this in a formula. And let's say I don't have Desmos, but let's say I have a formula. And this is actually the proper way of doing it, using 2t cubed minus 15. So let's just say that you don't have the graph going on, because I want to turn it off as a graph. I don't want to see it while I'm graphing. Cubed, but in your calculator you can fill out the formula, and this is faster than the technique I'm using, because once you have the formula in, you should just keep it around. Was it plus 10? Minus 10. Okay, and you got to get rid of any t's I accidentally put in there. I just use x to be simple. And then you can just do f of 1, f of 2, f of 3, f of 4, f of 5, f of minus 1, f of minus 2, f of minus 3, f of minus 4. And you can see that it's probably a half. Third, fourth, no. So it's essentially not letting me factor. Let me try 2, 1, 2, 5, 10. Interesting. I'll try, I'm just doing all the factors of 2 and 10. 1/10, 1 over 5, 2 over 5, negative 2 over 5, negative 2 over 10, negative 1 over 10. Interesting. So it's not factorable. So that means you're going to rely entirely on your charts. Okay. Let's see if we can find any x-intercepts. Will this ever equal to 0? Again, we'd have to factor it to find that out. There's a chance that I didn't factor it correctly. I don't think so. So we're not going to be able to find x-intercepts. We might be able to if we set it, find the derivative. But let's just continue the way we would normally. What happens when we figured out that? Let's take the derivative. 6t squared minus 30t plus 36. And we're going to see if that has, and I'm just going to jump straight to my quadratic function, quadratic calculator, and I'm going to put in, I could factor it, but I'm just going to do this, 6 minus 30 and plus 36, to see if there's any clean ones. There are. It's 3 or 2, which means I could have factored it. Oh, of course, I take a 6 out, and I get t squared minus 5t plus 6, which clearly means 6t minus 3 and t minus 2, which is what they were trying to. Now keep this first derivative around, so this is h of t, you'll need it. H prime of t is equal to that. And when we set it to 0, when will it equal 0? When t is 3, or when t is 2, which means this is a positive cubic. It must pass through the x-intercept at least once. It means it's going to either do 3 times, possibly, or just once, more likely, because I had trouble factoring it. And we're probably going to have to estimate where it goes through the x-axis, and that's still really important. But we do know that at 3, at 2, and at 3, there's either a max and a min. Sorry, I said min or max, or max min. So if we plug that into the original equation, we will get the points where that's a max or min. You could also take the second derivative. So we're going to take the second derivative here, and we get 12t minus 30. And when you set that, so that's x double prime of t. And when you set that with the numbers that you found before, so 3, you get 36 minus 30. It's positive, which I believe means it's a negative, but which means it's a max, but I'm going to just confirm that. And when I set for h double prime of 2, I get a negative. And I just kind of sort of hazy on when it's a max, but what I'll do instead is plug 3 or 2 into this equation, and then I'll get the y values exactly of how to map it. So my guess is this example is teaching you more how to find the max mins. And I'm just going to put that down there too, so that I have the factored form in case I need it. So I'm going to plug in 2 here. I get 2 times 8 minus 15 times 2, which 4, which is minus 60. 2 times 8 I should just write down as 16 minus 60 plus 72 minus 10. So I can see minus 60 minus 10 is minus 70 plus 72 is plus 2. So I'm dealing with 18, which is a max. So that means when it shows a negative, it means the curve is turning around the other direction. So at 2, when I do my graph, I would put this nice little 2, 18 on my graph. And I know that it's going to be a max. Now I'm going to put 3 in there, because it could be 3's above the curve too. It'll tell me a lot. Oh, just want to get rid of these. So when I get 3 in there, 3 cubed is 27. 2 times 27 is 54. 3 squared is 9 times 15 is minus 135, I think. And then 36 times 3 is plus 108 minus 10. 108 minus 10 is 98. Minus 35 plus 90 is minus 45. And 54 minus 45 is 9. So that means it doesn't come back to the x value, which makes sense. It comes quite a ways down. And it's 3, 9. So that means I'm dealing with something, sort of like this. And like that. Just a little bit connected. And then it's going to go shooting off into space again. It's going to be a little bit steep. And, oh yes, it's going to cross through the y-axis we know here at minus 10. So we have to also label that, which tells us a lot. It tells us that somewhere between 0 and 2, it's crossing the x-axis. So I'm going to go back to the calculator, and I'm going to keep it off. I'm going to try f of 0, f of 1. Oh, we're positive. F of 0.5, we're positive. F of 0.2, we're negative. F of 0.3, we're negative. 0.4, positive. 0.35. I'm going to try f of a third. Positive, okay. F of a quarter, negative. F of 2/3, positive. F of 2/4, F of 2/5, F of 2/10, no. So somewhere between 0.4 and 0.3, it goes through the x-axis. You might say, well, what do I do? Do I just keep calculating numbers? And no, you just try to give a guesstimate. Is it point? I already did 0.33, I think. Yeah, it's not 0.33. It's 0.16 or 17 or 18 or 19. Getting close. Yeah, 189, 8, 7, 6, 5, 4, 3, 2, 1, 2. So it's somewhere around there. It's like, and you can see that that's not really a decipherable number unless I missed something in my calculations. So you're not going to get a clean x, except that to notice that it's somewhere quite small. It's somewhere around a third. Now, you don't have to label it, but you should sort of measure, as I did, what happens on this side and this side to get a roughly idea. So what you do is you plug 1 into there, and when you plug 1 in, you get -1 minus 2 minus 15 plus 36 minus 10, which is minus 25 plus 30, so you get 7. So it tells you that 1 comma 7 is positive. So you know that it crosses the x-axis somewhere between 1 and 0. And that's easy to calculate and to mark on your graph. Why not? And you would then, if you really needed to, which we don't in this case, construct a table. If you didn't know how to do second derivatives, you'd use your first derivative at 1, which we had as, this was our first derivative. And you take a number that's just to the left of what you know is the peak. We know the peak is 2, so if we took 1 in here, we discovered we had 6 times a minus number times a minus number, so it comes out as positive, which means the slope is positive on this side. And if we took a number at 2.5 here, 2.5 here becomes negative, and here becomes positive, so the number becomes negative. So we know the slope is going down on this side, which tells us it's a max. So if you didn't know how to take second derivative, you just use first derivatives on either side to see that the slope's going up on this side and down on this side, which will tell you if it's a max or a min, if you don't know how to set second derivatives. Second derivatives, incidentally, will also tell you when they set to 0, tell you the inflection point. So if your teacher wants to know the inflection point, you've got to go back to your second derivative. And I foolishly didn't write it down. I think it was 6t squared minus 15t plus 36, which means that the second derivative is 12t minus 15 or minus 30, minus 50. 6t squared minus 15t, yeah. If you set that to 0, you will find your inflection point. Divide them both by 3. So that means that x is equal to 1 1/4. This curve, is it 1 1/4? Is that really the inflection point? 1 1/4, this curve is going this way and starts to turn around. It actually should have been on this side, so I did something wrong in the second derivative. I'll point out the inflection point on the graph. So now we're going to just click this. We're going to make it a little bit more visible by making the x-axis go down to minus 15 and up to 5044. There we go. Then we're going to put in 2 comma f of 2. Why isn't it letting me do it? Oh, 2 comma f of 2. And put it in a bracket, and that'll let me label it. And we're going to do 3 comma f of 3 and put it in a bracket. That'll let me label it. We're also going to do 0 comma minus 10. We're going to label it. And we're going to find the inflection point. When does f double prime of x equal to 0? And there's the inflection point. So I actually calculated it wrong. So I had the second derivative wrong. It's at 2.5. Now what is the inflection point? The inflection point is when a curve, like a ski hill, I want you to imagine a ski hill here. You're on top of a ski hill, you go down, it curves, and then it goes flat again, right? Well, that means this ski hill was getting steeper, 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 and at some point around there, it started getting shallower and shallower and shallower. That's called an inflection point. It's when the slope of the curve changes directions. So it's essentially when it becomes, goes from, I forget what we determined. It will change signs. The second derivative will change signs on either side and will equal to 0 at the inflection point. Well, in this case, by setting my double derivative to equal to 0, I've discovered the inflection point is at 2.5. So I'm just going to label that 2.5 comma f of 2.5. And put a bracket. And you've now also found the inflection point. Notice that the x-intercept is indeed not decipherable. It's 3.18. So there was no really factoring to be done. So you could not figure out the exact inflection. However, this was a cubic, and you know the behaviors of the cubic. Start in quadrant 3, end in quadrant 1. You found the min-max local points. You found the y-intercept. You already know what it does, so you don't have to construct a table of intervals, although you could if you wanted to. And we can see that this turning point never crossed the x-axis again. Came up with a pretty accurate graph, and that's all your teacher would expect. And you should put in your calculator what happens when it reaches negative infinity. It's equal to that. Now, that's tough to do on these ones. You just essentially figure out what happens here. It's 2 times infinity cubed minus 15 times infinity squared plus 36 times infinity. And it's quite clear that infinity cubed will trump all of this by far. And thus, this end is plus infinity. Now, you don't need to do that for these graphs because you already know the behavior of cubics. But if you wanted to show that it's clear that this will be negative infinity as x approaches negative infinity, y approaches negative infinity. But again, the nature of cubics already tell you that. You pretty much have maxed out the graph for this one. And really, these things are easier to graph than rational functions. I'm surprised it's in there. So this one's also, you might say, going to be difficult. But look at the bottom. That can never equal a 0. When can x squared equal negative 4 to create a 0 here? It can't. So that means this entire graph, because this is a positive integer, and this is always going to be positive up here, y is always going to be positive. It can also never equal to 0, because if you set it to 0 and then bring this to the right side and it disappears, 20 equaling 0 can never happen. So that means it never crosses the x-intercept, which means this entire graph, if that's the Cartesian graph, it's always going to be positive. So the question is only like, when does it sort of become close? What does it look like? I happen to know that these graphs look like that. The question is where this hump occurs. And for that, you might want a second derivative or first derivative to figure out any peaks and valleys, because some of them also dip down a bit, come up, and dip down a bit, depending on what the factors are. So in this case, it's more about derivatives. You can also set x to 0. So when x is 0, we got 20 over 4, which is 5, which means you have an y-intercept of 0, 5, which is a great place to start. So we're going to do our graph, and right away we're going to say it goes through 0, 5, which is quite high up, isn't it? So you just need to figure out what happens after that. So what happens at 1? When this is 1, this becomes 1 plus 4, becomes 20 divided by 5, which becomes 1, 5, which actually tells you a lot, or 1, 4, which tells you a lot, which means it's kind of going up from here, kind of going up. So really it's just about finding the peak after that. To find the peak, we're going to find the derivative. This equation here is the same as this equation, 20 times x squared plus 4 to the negative 1. To the negative 1. It's the same thing. And don't forget that you have a squared here because it'll matter. Oops. Now, in the product quotient, you take the derivative of this times that. Well, the derivative of a number is 0. So derivative of the first part will just come out 0. In the second part, you take 20, and you multiply it times the derivative of that. The derivative of that, if I take it separately as f of x, you do the chain rule. You bring the minus 1 down. You get x squared plus 4, and you lower this up here to minus 2. And then you take the derivative of the internal. The derivative of x squared is 2x, which means you're going to get minus 2x as the numerator, and on the bottom you're going to get this squared. That's what the negative 2 is. So all of this here, this part here, becomes the numerator, and this part here becomes the denominator. So you're just going to get 0 plus this mess. So that means the derivative, multiply by 20, because remember it's 20 times that. So you get 20 times that, you get minus 40x at the top. Okay. So the question is, that's the first derivative. We figured it out. We need to figure out, when is that first derivative ever a max or a min? How many does it have? Well, when you set it to 0, you get rid of this part by multiplying it by x squared plus 4 squared over 1 on both sides. It cancels out here and becomes 0 here. So that's why the numerator is really the only thing you have to worry about when you're figuring it out. I'm just going to keep the derivative over here in case I need it. So that means when is minus 40x equal to 0? Well, when x is equal to 0. There's only one of them. When x is equal to 0, we've already figured out this occurs here. So I'm going to suggest that it's probably going to do something like that. And this is going to be the peak, which means it's probably got a minus 1, 4 over here as well. So let's try that out. When we put minus 1 over here, it also becomes a 4 because it's the same minus 1 squared, which means every dot over here will be mirrored on each side as I go out. So you're going to have a perfectly symmetrical through the y-axis, which is called a even. I think it's called an even function when it mirrors on the y-axis throughout. The only question is, what happens at infinity? So when you get 20 over x squared, you can either factor out. Sometimes you have to. In this case, you don't have to. It's clear that it's just going to be 20 over infinity squared. Any number over a huge number will approach 0, but never reach it. What happens at negative infinity? Well, negative infinity gets squared. So it becomes positive infinity again, so it also approaches 0, which means this whole graph is going to try to hug the x-axis as I go out. You can find a couple other spots if you wanted. You could plug in 2 here. It becomes 20 over 4 plus 4, or 20 over 8, which is the same as 10 over 4, which is the same as 5 over 2, which is 2.5. which means here at 2, you're going to get 2.5. And here at negative 2, you're going to get 2.5, and so on. But if we graph this, we're going to get exactly what we expect. We take a couple table values, and we can indeed see exactly what we anticipated. And we can even take f of 1,000,000 here and see that it's getting very close to 0, but f of 1,000. And same with f of negative 1,000. Very close to 0. As I add more zeros, you'll see that 10 to the negative 7. That just means we're getting even closer to 0 as that negative number gets bigger, 10 to the negative 15. So we can see we approach 0 and never get to it. You can prove this graphically by zooming in on a point. Looks like it's touching the x-axis, but as you zoom and zoom, you'll see a space. Never gets there, and that's because 20 divided by infinity will always be a number slightly above 0. There you go. Just click your home key when you want to go back to the graph. And you discovered a lot. That was the only maximum. So the only maximum possible. The derivative told us that, so there's no need to take a second derivative because we knew the nature of this graph. By taking a point on either side, we saw that it was a maximum. Mind you, you could set the second derivative if I wanted to do that. The second derivative of this up here, you'd have to take the quotient, do the quotient again. So it's essentially going to be this times the derivative of that, which is now to the negative 2. Or you could do the quotient method too. But I like the product rule when I'm doing this, plus the derivative of that, which is just minus 40. So it's good to just keep it in brackets. So this next one is just going to be minus 40 over that, because you don't take the derivative from that one. And it's just a question of finding the derivative of this. It's obvious to me, anyway, that one of it's going to be down here to the negative 3. There's no need to do this, by the way, negative 3. And then I would simply continue. This is negative 2 times that, so I get 80x up top. And then it's going to also be times the derivative inside, which is 2x, so 80x times 2x. I'm going to be left with 160x squared. Then you'd have to make their denominators the same in order to add them, blah, 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 blah. You're going to come up with an equation. But you can see sometimes taking the second derivative is tough. And I set it to 0. Oh, that's going to give me the inflection point, so that's when the curve. That might have been worth finding out. Depends if your teacher wants inflection points, and that's when the curve essentially started turning around. And then what you do is you find the double derivative of 0, and it'll come out negative, which tells me we're dealing with a maximum. So negatives are maximum, positives are minimum. And when you find out when the second derivative is equal to 0, you find out inflection points, because this ski hill was steep, steep, steep until there, and then it started shallowing out. Steep, steep, steep until there, and then started shallowing out. So we could have, I think setting it to 0 would have been tough to find out, though. You can see that these graphing calculators are a much better tool. We still graphed it as well as I think your teacher wants you to at this stage. This one's interesting, and like I said, I'm just going to do number 10 and then stop, because it just takes so long to graph these. The best thing you can do here is put them on the same fraction. So obviously, oh, I should have just done it like this. There we go. Obviously, that first one is t over 1. And the second one is 1 over t. Well, how do I get a t down here? I have to multiply both this left fraction by t over t. So I get t squared over t. So that means this just becomes, if I move it up a bit, t squared over t. If I multiply it by t over t. Now I have the same fraction, so clearly up top I'm dealing with t squared plus 1 over t. Now, when you're taking the derivative, it actually might be easier to keep them as separate fractions. But essentially this here is the same. If you put both of these into Desmos, they're the same graph. So ask yourself a couple questions. Do we have any vertical asymptotes? Yes, we do. So you can draw here, and you can see that when t is equal to 0, we're going to get a vertical asymptote. So again, you could make a couple holes in it, but because it's on the x-axis, you might not want to do that. But you could also label it that t is equal to 0 is a vertical asymptote. What about a horizontal asymptote? Well, we have t squared over t, and that is actually going, because this is bigger, I believe creates a horizontal asymptote, or a vertical asymptote. And to figure out what that is, you actually factor in, you actually do long division, old school functions, and you multiply this by t, you get t squared plus t. This plus 1 is essentially a numeral, so there's actually a plus 0t here in the middle. When I subtract them, these cancel. I get minus t. To get t to minus t, I have to do minus 1. That's all you need to do. So that means the line t minus 1 is the equation of the what is called an oblique. I think it's called an oblique. Forget what it's called. The diagonal asymptotes is when the power up here is 1 more than the power down here. Then you do long division, you come up with this equation. This will be the equation of the diagonal asymptote. And you can label it. Y is equal to t minus 1. And, you know, diagonal asymptote. It has a different name. And that only occurs when the power is 1 more. Now, what does that tell me? Well, if you just basically look at t squared divided by t, you can see the result's going to be a t. So it's essentially a line, t plus 1, that's going like this until it hits this asymptote. Then it goes zoom. Then it's going to do this and like that. And the only question is, will it ever cross the diagonal asymptote? And that's how I know this, because that's how these behave. Now there's a chance it might be on this side. It might cross and then come down, and then it might be on the top side. It might cross, and you have to figure that out as well. So to see if it ever crosses the line t minus 1, you make it equal to t minus 1. You bring this t up, you get t squared minus t squared plus 1. So there you go, t squared minus t, yeah, that's important. So you're left t squared plus 1, t squared plus 1 is equal to t squared minus t. You bring the minus, or just leave the minus t there. You bring the minus t squared to this side, it gets rid of it. You get minus t is equal to 1, or t is equal to minus 1. So that means when t is equal to minus 1, this does indeed cross that line. So let's figure out when that is. So when t is equal to minus 1 up here, we get 1 plus 1 over negative 1, which is negative 2. So at negative 1 comma negative 2, which helps us a lot, we know it'll cross the diagonal asymptote. Now I like to keep this equation clean, and unfortunately I didn't. I'll try to keep it over here. Let's also find out when t is 0. Well, we've already discovered that can't happen, so there's no y-intercept. It might help if we plug in t is equal to 1, just to figure out a couple points. We get 2 over 1. So when the t is 1, we get 2. That helps us a lot, actually. Just to have a couple points. And we've already discovered it crosses at t minus 1. So the big question is, what will happen to the left side here? Does it go on this side of the asymptote? Or, so we would take a value very close to the asymptote to see if it's on this side. Because we know it crosses at minus 1, we would take like minus 0.1. 0.1 to see if it's way up here or way down here. So if I take 0, what's to the left of 0? Negative 0.1. Negative 0.1. When that squares, it becomes positive 0.01. When I add 1, I get 1.01. Down here, it's still negative 0.1, which means this whole number, when I divide by a point, it actually makes this negative 10.1, which means I'm in the negative realm, so I can tell that it's sort of going to come up like this. It's going to cross the asymptote here, but then it's going to hug it, because it's not allowed to cross again. We've only determined one crossing point. So now I know my graph in blue, because I took a value very close. It's going to come up, come through here. And really, to do this, you should do your table of charts. So I'll just keep doing it. We also know it does not cross the vertical asymptote again on this side. So if I take positive 0.1 on this side, I get 1.01 here divided by positive 0.1, and I can see I get 10.1. So it's definitely going to come down like that. It's essentially trying to complete a line this way, and then boom, the asymptote interferes, and then it's coming up the asymptote here, barely crosses, and then continues along its line path. And that's what these things tend to do. You should find now, clearly there's a max and there's a min, so we should find the derivative. You should also make a table of charts to make sure this is what's going on. And your table of charts would look like this. You'd say, I'm going to test negative infinity. I'm going to test just to the left of smaller than negative 1 to see what side of the line I'm on. I'm going to find between negative 1 and 0. I'm going to find just to the right of 0. Just to the right of 0. And then I'm also going to find positive infinity. So you should construct a chart like that, and then you should put the original things in there to see what they become. So negative infinity becomes positive here, negative here, so I get a negative. And it's going to be infinity. When it's just to the left of negative 1, let's say negative 2, I get 4, 5 here, and over negative 2, so I get like negative 5 over 2, which is negative 2.5, so it's somewhere around there. When I take, I think I said like negative 0.5, I discovered it becomes positive, negative, like infinity, as I get really close to 0. Slightly bigger than 0, I've already discovered it's positive, and you just put it into here. And you discover, positive, and you discover negative. And then positive infinity, this becomes infinity squared. To take positive infinity, you factor out the t squared, you get 1 plus 1 over t squared. And you get t and 1. So it's clear that this doesn't matter. This becomes just 1 as infinity gets huge. And you get infinity squared divided by infinity, which is infinity. Let us now work on the derivatives, because that's more important. So I've got t squared, and this is where taking this derivative might be easier using the sum rule. And that is because we're dealing with t plus t to the negative 1. So all we'd have to do is the chain rule. So the derivative of this, what's the derivative of t? It's 1. What's the derivative of this? Well, you get minus 1 times t to the minus 2 times the derivative of t, which is 1. So you get this. So you get 1 plus negative 1 over t squared. There, that's our first derivative. All we do is we have to set it to 0 to figure out what values will have a max or a min. So we're going to start by multiplying it by, or subtracting 1 from both sides, multiplying it by t squared. So I get negative 1 t squared is equal to negative 1, dividing it by negative 1, so I get t squared is equal to 1. If I take square roots of both sides, I discover that at t1 and at t negative 1, I get a max or a min. Well, I've already discovered that they're going to be max, min here and max here. And I've also already discovered that it's 1, 2 and negative 1, 2, 1, which means it just touches this and then starts heading down. And it means it just comes to here and then goes zipping up. So right there, using the derivative, and then you take this 1 and minus 1, you plug it back into the equation to find your values. You've discovered the max and min, and there's 2 of them. Let's go look at this equation now. So the original one is t plus 1 over t. T plus 1 over t. F of t. Get rid of this. Now, let's draw the line y is equal to x minus 1. It does exactly what we thought it would do. There's the max, there's the min. I'm going to put it in a table form up here so that you can see the max. There's the min, there's the max. There's another value that they're throwing in there, which I think we did as well. Notice that they're a perfect mirror. They're an odd function. It crossed its diagonal asymptote. It was important to find that diagonal asymptote. We found that there was a diagonal asymptote because we knew the power above was 1 above the area. We also set it to the diagonal asymptote to see if it crossed the diagonal asymptote. We knew that there was no x-intercepts. We knew that there was a max and the min from our derivatives. We graphed it about as good as we could. We can also see that if we take f of 0.0001, we get a positive infinity number. If we take negative 0.01, we get a negative infinity number, essentially. If we take a negative infinity, it's just going to approach negative infinity, and same with positive infinity. Okay. And how you write that down on the paper is, as x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches negative infinity. Some do the opposite. That's how you write it down graphically. Okay, we're going to just keep going. Not the one I was working on. There we go. So we just did those two. We're left with this. Now it's getting tough. Now, the first thing you should always see with these numerators is if they're factorable. It'll save your life. Save you a lot of headaches. And it looks like this one has some domain conditions. They're not going below -7. So that means you're only going to graph -7 and above. But let's focus on this. It does 2x squared plus 5x have a factor? Well, does a number that multiplies out to 4 add up to 5? 4 and 1. So but you can't use x plus 4 and x plus 1 because there's a 2 in front of that x. So you have to use the slip and slide method, which means you divide both by 2. This becomes x plus 2. This can't divide, so it goes in front. So the factors up top are 2x plus 1. You can go ahead and look up the slip and slide method. It also saves you a lot of time. And down below, it's clear that we have an x plus 3. Now this is definitely one where you're going to set up tables for all these factors. Right away, just hunt out your vertical and horizontal asymptotes. This is one more than that, so we're going to have a diagonal, I think it's called oblique asymptote, and you just simply do long division into that to discover what it is. But let's first find our vertical asymptote. Our vertical asymptote is obviously x is equal to minus 3. That's because when x is minus 3, the bottom becomes 0, which cannot happen. The denominator can never be 0. I put a hole in the x-axis, that's fine. And you would mark it, x is equal to minus 3 is it's the only horizontal vertical asymptotes, which is great, which means you're dealing with something like that. You just have to figure out if it crosses anything, and I was mistaken about, yeah, it still might have a diagonal asymptote. But this is a good one to start. The next one is, because the power is bigger, you're not going to have a horizontal asymptote. You're going to have a diagonal one. So it's important to figure that out. So do long division. If you're missing any x factors, you put it in, but we're not missing any. And you do just like a normal long division. How many times what do I have to multiply x by to get 2x squared? 2x. When I multiply 2x times the x, I get 2x squared, but what happens when I multiply the 3? I get plus 6x. When I subtract this, these cancel out, and I get minus x. What do I have to multiply x by to get minus x? Minus 1. Stop. You've got your line. It's got a slope of 2, and it's 2x minus 1, which now means you have your oblique asymptote is 2x minus 1, so it goes through minus 1. So you can even tell that it goes through minus 1 here. This is if the slope was normal. It's quite clear the slope is going to be twice as big. So you're looking at something like, little inaccurate, but you're looking at something like that. Not quite, but like that, which means you're going to have it maybe cross or maybe hug like that. It might just cross and then hug. You have to see if it's crossed by seeing if this ever equals that. So let's see if that can happen. This, as we've already discovered, is this. Does it ever equal this? Okay, we start by multiplying both sides by this. It cancels out here. We get on the right side when we expand it 2x squared plus 6x minus x plus 5x minus 3. Well, we already know the expansion on the left side is very much the same, which means when I subtract to the other side, they'll just cancel each other out. And I'm left with 2 is equal to minus 3, which we know makes no sense, which means it never crosses that asymptote. The question only remains is, which side is it on? So here's where you take your table. Oh, you should also see if there's any peaks and valleys. So we're going to now take the derivative of this. Now I should use the quotient formula because it is faster. However, I find it easier to take the there it is there. I find it easier to take the product rule, but that's just me. So here's the quotient rule, but I might as well do it. So here we go. So again, I'm just going to get rid of these. Oh, maybe I shouldn't. I'll just put this one up high. So there's the quotient rule. So that means you have to define one of them as g of x. This always helps, by the way. Define one of them as g of x. So we'll make this our g of x, even though I know the whole thing is g of x. And we'll define the other one as f of x is equal to x plus 3. So that's just the denominator. Then we'll just fill in the blanks as we see it. So we have to take this here and multiply by the derivative of this. So the derivative of this is simply 1. When it's like that, it's easy. So that means we're just left with this on the left side. Then we have to subtract this times the derivative of the second one. What's the derivative of 2x squared plus 5x plus 2? You can pretty much ignore the 2. It is 4x plus 5. Go learn your product rule. And all of it will be over g of x squared. Yeah, but in this case, the g of x is the... Oh, yes, we must do it in the proper order, by the way. So I made a little error there. This should be the f of x, and this should be the g of x. It does matter, because otherwise your symbols will not match. So in this case, you must make sure your g of x is indeed your denominator from the equation. So that means I have to multiply my g of x on the numerator. I could have just switched their orders, times the derivative of my numerator, which is 4x plus 5. And then I have to subtract, and in brackets, take my numerator, which is 2x squared plus 5x plus 1, times the derivative of my denominator, which is 1. And I have to put it all over my denominator squared. Now, it looks like a mess, but it's okay. You now expand x plus 3 times 4x plus 5. You get 4x squared plus 5x plus 12x plus 17x plus 15. We can now remember, though, that this minus has to apply to everything in the bracket, and that's a common error. So you got to do minus 2x squared, so this becomes 2. So it's 4x squared minus 2x squared, minus 5x, so this becomes 12, plus 15 minus 2, so this becomes 13. So that means I have to rewrite my denominator as 2x squared plus 12x plus 13. So that's now my numerator. Now the nice thing is, get rid of the quotient rule. The nice thing is, the numerator is the only thing that's going to matter to finding the max min. Because this is now the derivative. And when you set it to 0, and you get rid of this 0, and you set it this by multiplying it by x plus 3 squared over 1 on both sides, disappears here and becomes 0 here. So it's essentially you're doing this. When will this equation equal 0? So does it have any max mins? So now we have to factor this new thing, and the question is, and sometimes you have to use the quadratic function, but the question is, do we have two things that can multiply out and achieve 26, if I got my numbers right, by the way, and add up to 12? Well, they're going to be fairly close, and it's all positive, so they're all positive numbers. So you've got plus 13 and 2. That doesn't work. And I don't think there's any close factors. So that means you have to take your quadratic equation. I should have kept all the things up. Quadratic formula. And you have to put in 2. Yeah, I hate that one. This one's a good one. So you have to put in 2, you have to put in 12, and you have to put in 13. And they come up with two numbers for us. Now, if I got the numbers right, I might have made an arithmetic error. It's quite easily possible. But they're telling me that this is going to equal 0 when t is, or when x is, either of these numbers. Which means I now should put it into this equation over here to figure out the y values. Okay? So if I got this right, they're telling me there's sort of a rise or some sort of weird crossover at the minus 1.43, which is over here, and at the minus 4.56, which is over here. So it's going to come up and come down. You would normally take your graphics calculator or by hand, plug these numbers in. I'm not going to do it. I'm going to just take this formula and plug it in to figure it out. So I'm going to come back to here. I'm going to do an f of x graph. What? Why is it doing that? It's equal to. And I'm going to start writing in the original equation. I'm going to write in the factored equation, actually, 2x plus 1, but I'm going to turn off the graph, okay? So this is as if you're just figuring out some numbers. And we're going to do x plus 2. And I might have to stop after this. X plus 2. And it's all going to be divided by... This is what happens when you don't do it properly. It's all going to be divided by x plus 3. So I'm going to just set my first derivative equal to 0, and it's going to tell me exactly what we found out before, right? That we're dealing with f of negative 4 point, what was it? Negative 4.5811. And I'm just going to label that negative 4.5811, comma that. I'm going to label it. So we're going to see, oh, it's going to be way down there, yeah. And I'm going to also do the negative 1.5811, comma f of negative 1.5811. And I don't think I got the number quite right. It's negative 41886. 41886. And I'm going to label that one. So we're going to find those on the graph as a max and a min. The question is, how do we graph it? Okay. Now we set up our tables. We have our factors. We know an asymptote. And you're going to have to set up, well, I'm just going to make this whole thing a bit smaller. No. You have to set up a table. You should figure out when it's negative infinity. Okay, you should also figure out, we should stop making the same mistakes. What's our negative, you can figure out something just to the small left of the asymptote. You should figure out, by the way, we determined it never crosses the oblique asymptote. You should also figure out when it's between, let's see, what would be, there's no other things, but you should see when it's between, like, just slightly bigger than minus 3. And there's no x-intercept. Or did we figure out if there was an x-intercept? We never did we? You'd have to set it to 0 and ask yourself, oh yes, we figured out 2 x-intercepts, the numerators. I never got around to it. So when is the numerator going to be equal to 0? When x is negative, and that's very important. That's what I forgot. When x is negative 1/2, one of those up top becomes 0. And when x is negative 2. So that means right here, at -2, 0, and I need the numbers smaller, or the graph bigger, and it's just to the right of the asymptote, and -0.5, 0, it's going to cross the x-axis, which means I have something happening here and here, which means it either comes down and then goes up, or comes up and doesn't make sense that it would do that, so most likely it's going to do this. I remember that there's a little min we figured out right about there, and go up. So right away I already kind of know what the graph is going to look like, and I also know it's going to do that, and it's probably going to do this. It's going to come from up top and go down. So like that, and the line is going to sort of match our oblique line. So we have to add extra values in here, smaller than -3, but what happens between -3, smaller next, and -2? Is it positive or negative? What happens between -2 and -0.5, which is the next intercept? What happens when it's bigger than -0.5? And you have to finally add a positive infinity. Wow, see, so our chart is a lot bigger than we thought. Now some of these I've already answered just from knowing how the graph behaves. I made a big mistake not finding the x-intercepts right away. And there's this one, and then there's this one. And then you want to put a chart up here. Yeah, I don't really need that chart up there, I don't think. Well, you can put a number in there, actually, if you wanted to. And I'm going to put all the factors down the left side. So I'm just going to, and I'm going to kind of ruin my graph here. So I've got to put each factor down the left side. And figure out what happens. Now, when it's negative infinity up here, this still becomes positive 2 times the infinity divided by negative 1 infinity. So it becomes -2. So it's a -2 times infinity. So that means I'm talking about a number that's way down here. Because when it's negative infinity over here, it becomes positive, and down here it stays negative. So I'm talking about -2 infinity squared times, or +2 infinity squared divided by negative infinity. So it becomes positive, sorry, this negative divides in, it becomes -2 infinity, which is essentially negative infinity. So when it's negative infinity, it goes down to negative infinity, which means it's way down the graph. So that means it's going to be way down here, hugging the line, and then climbing up the asymptote. Well, no, actually, because we determined a max, it's actually going to probably turn around and come down. Then when it's smaller than -3, let's say -4, this becomes negative, this becomes negative, and this becomes negative. So that becomes negative. So it's still on the negative side, just to the left of the asymptote, still on the negative side. So it's probably doing that. But remember, we found a max. Then, in between here, what's a good number? Oh, -2.5. So this becomes negative, this becomes negative, and this becomes positive. So this becomes positive, which means in between 2 and 3, it's positive. So we have a graph like that. So I'm going to say it's looking again. It's going to come down through the x-axis, come up, and then hug the line. And then this other one, I've determined that it's negative. It's going to come up here. It doesn't cross. It's going to go like that. And we determined there's some max values and min values right there. So it's going to look like a line that's trying to follow our oblique line. It never crosses the oblique line. It does have some min-max we determined here. It does have x-intercepts. If I keep going, what's a good number to use for this? It's to the left of the x-intercept, -1. So when it's -1, I get minus, plus, and plus, so it's minus. So it means between the two intercepts, I dip down to the minus, which I hit my min point, which makes sense that we've drawn right there. And then finally, when it's slightly above -1, so 0, when it's 0, I get positive, 2, positive, and positive, so it's positive. So that means anything to the right of my x-intercept here is going to be positive. And then finally, positive infinity, I get 2 times infinity squared over infinity. It clearly becomes 2 infinity, so it becomes positive infinity. Let's turn on the graph. Oh, let's also put our oblique line in there. We're going to do y is equal to 2x minus 1. We're also going to put our vertical in here, like that. And finally, we're going to turn on our graph, and we're going to make it black. And we're going to get rid of these. Okay, notice we found the max and mins. Notice we've perfectly found the diagonal asymptote and the vertical asymptote, and it did exactly as we had hoped. I'm going to have to stop it here. I'm just out of time. As you can see, these things take a long time to do. But we only have this last one to do here. It does only have a one vertical asymptote. We should see if this can be factored. What's a number times -21 that adds up to 4? They're going to have to be close together. We can have -7 times 3, which works. So +7 and -3, which means the top part factors. Maybe I can do it quickly. Top part factors to x plus 7 and x minus 3. And the bottom is, I'm just going to keep it as x. I know it's t. X minus 3, and we're only dealing with numbers that are above or equal -7, so we've put a restriction on the domain, which means on your graph, you should find the -7 number. So when it's -7 squared, it's 49, minus 28, minus 21, so it's -49, so it's 0. 0. And down below it doesn't matter. So that means it's 0. At -7 x, it hits the x-intercept. So -7, 0 is one of the x-intercepts right there. What's the other x-intercept? It's when the numerator is equal to 0, and that's when x is 3 as well. So there's 2 of them, there and there. Just remember that we're going to not draw the graph to the left side here. It's going to stop right there. What's the vertical asymptote? It's when t is equal to 3. Oh, so we got a problem. Because this factor here matches here, we're going to have a hole there. Because you see how they cancel out? So really we're talking about a line, x plus 7. So it's going to go through like that. And at 3, because that's both an x-intercept and it's been canceled out, we're going to discover a hole at 3, 0. It's not going to go through the x-intercept. But you can see from the factoring that I just did that the x minus 3 cancels out with the x minus 3. And therefore, we're left with x plus 7, which is just a line that goes through -7, 0 and 0, 7, because that's the y-intercept. And when it hits this 3, 0 or 3, whatever it is supposed to be, it's 3, 10 normally, actually, because if I put 3 in there, I get 10. It will have a hole. It's not the x-intercept. So all we're dealing with here is a line that has a hole. We don't have to do, there's no max or mins. And right away when I factored it out, I should have seen that these two factors cancel, which creates the hole at 3. At 3, when I plug it into x plus 7, it's 10. I can also see that when x is minus 7, we have an x-intercept, and the y-intercept is 0, 7, and we're done. That's all it is. So we're going to put that in as the expanded form. And sure enough, we're going to see exactly as we anticipated. Whoop. I'm going to just do 0, 7. And 7, 0. Whoop, minus 7, 0. So that you can see the 2 points. And if we zoom in and go to 3, 10, we're going to see undefined because it creates a hole. So when you draw it, you got to put that little circle with an empty hole in it. The last one was quite easy. I was just a little bit slow. And that's it for now.